Hello friends, welcome back to my channel. Today we are going to discuss about structural indeterminacies of trusses, specifically for trusses. So first of all, we need to recall few information which we have already know, but they are quite related to this topic, so I'm repeating them. And first of all, what are the types of structures? What are the various structures? So there can be, depending on the members, how they are transferring the load, there could be a truss member, or there could be a frame, or there could be arch, or there could be a structure which is a cable. Okay, there could be a cable. The structures are truss structures like this. Could be a truss structure which could be supported like this is a hinge. This one is roller here, you can support it. It is a determinate one. I'll tell you what is a determinacy first of all, but before that we are going to discuss these few things. What is these type of structures? The truss. So truss is some this kind of structure which transfers the load only in either compression or in tension. This could be a compressive force. I noted. I can. I just. I just wrote this letter. This is a compressive force. You are compressing some member. There is a tension. So you are applying a tensile force to elongate it, or compressive force to compress it. So there could be compressive or tensile. In trusses, few we have few assumptions, like if those things are true, then the member will subject only these axial forces. So truss is just something built up by the members which are only have axial forces. And what should we assume in order to get that particular situation is that first of all, whatever the structure we are using for truss, the connection of the members of that structure should be pin. See, this is a pin and single pin is passing through it, so it is not restricting any rotation. This is idealized. Sometimes you have seen so many truss structures, they use multiple pins, and since they use multiple pins, the rigidity of the joint is no more allowing rotation it offers resistance against rotation. Like this is not offering rotation. This is offering rotation, and since it is not resisting it, it is not restrained. Rotation is not restrained, that's why it is not resisting it. Okay, so similar, all joints are assumed to be pin connection, only one pin passing through to allow the rotation. Okay, first assumption. Second assumption is the force which is being transferred. See, the force which is being transferred between, say, these two pins is acting along the centroid of the cross section. Right now I'm not showing you how it is, how its cross section would look like, but you can imagine it something like this. Suppose this is the member which is continue, sorry, this way, that was, this is not don't consider this as this structure. I'm just showing you a rectangular cross section which is homogeneous and prismatic throughout the length of this member. And see, I'm assuming that this is a member and I'm just showing you the cross section. Assume it is a rectangular. Okay, although it is not rectangular, but you can assume it. So this is the cross section of it. Okay, so assume it is a rectangular one. This portion is not there, assume. So centroid of that cross section will somewhat look like rectangular, and I'm just pointing out the centroid of the this cross section. This is the cross section. The force must be transferring in this fashion. So force is being transferred in this fashion or in this fashion. Okay, so what it gives us, but these, what are the advantages of these two assumptions? The first assumption, which we assumed that the all forces are being transferred through the joints, it tells us that there will be no force acting on in between those um, in between those points. Okay, yes, first of all, it is not offering resistance. First assumption. And the advantage of these pin joints are that this, at this joint there will be no rotational resistance. There will be no rotational resistance. Okay, so what will be there? The resistance will be only, resistance will be this, but not this. This one will not there. So there will be resistance offer in two mutually perpendicular directions. Suppose you can say this is y, this is x, then what will be the direction of the force or reactions will be resolved in these two components. So there will be only forces which are mutually perpendicular, they will act there. The advantage of first assumption, that these are pins. What is the second assumption? We assume that force is being transferred through the centroid, and what it gives us, that if I am applying a load somewhere there closer to the bottom section, then the force will be somewhere there, and if I apply a low force in that direction, you can observe there will be some bending in this cross section. See, I'm just holding this is from, see, the lower fiber is being compressed and the upper fiber of that cross section is elongated. Why this happened? Because there is acting a moment. And what is the magnitude of that moment? The force which I was applying, say P, the P is the load which is being transferred through this cross section. Then if it is acting somewhere below or above the centroid axis, centroid of that cross section, say at some eccentricity, say E, then there will be a moment, there will be some moment whose magnitude will be equals to P times E. Okay, so what kind of this is? This is a hogging type moment. I'm applying a compressive force in the near to the bottom layer, not at centroid. You have seen this example in pre-stress structures, pre-stress girders. What happens when these structures, this pre-stress structure, then when load comes to it, it just straight downs, and without it, it will just sag. Okay, so we apply some hogging moment, and that is counteracted by the load when it occurs on the structure, and it just releases some stresses, and there will be net there will be lesser amount of sagging, or say almost zero amount of sagging, because we have already applied a hogging moment, and that is counteracted by the application of the load. So that is something which we are avoiding in discussion of trusses, because we are assuming that all the forces which are being transferred are not acting at any eccentricity. We are assuming that this eccentricity is zero, so that's why the moment will be zero. Okay, getting? So there will be no acting moment in the truss members, only the axial force will be acting. Our second assumption. What is our third assumption? Our third assumption is that no load, or in other words, uh, all the loads are only will only act at the nodes. Suppose this is a member, and these are the pin joints, and as I'm just using, say it is a node 1 and it is a node 2, which are the extremes of these two members, not extreme but the position of these two connections, the hole on this member. So what will happen if a load will act on, say, in between these two nodes? This member will sag, there will be some bending, and we are discussing about trusses. So in trusses, we assume that there is no rotation resistance against the rotation, and we assume that we know that all the members are facing only compressive and tensile forces. So we don't wanna apply some moment on the member individually, and that and that particular member will not be, and we will ensure that that particular member is not going and undergoing some bending. Okay, So if there is a bending, there will be bending stresses, and we are not discussing them in analysis of trusses. Of course, when we construct the truss structure, we assume that all the when we construct before secondary analysis of the trusses, secondary analysis of trusses, we rigid these pin joints and analyze them as quite rigid joints, and can remember such a structure is frame structure with rigid joints. Okay, it offers resistance, but pin joint do not offer, huh? So when we discuss about the frame structures, we will apply some bending load can be applied in between these two nodes. But in the discussion of trusses, the loads will always be transferred or applied through the nodes. Okay, see, mm, these all will act along the node. Say this is and node 1 and this is node 2. All the loads will be act on these two nodes. So we know that in this case, if there is a no load acting on it, it will sag. Why? Because it has its own weight, which will which can be analyzed under a UDL, uniformly distributed load, between these two nodes. And if this is properly supported, say if it is a simply supported, then there will be some bending over it, and that will be something like parabolic. You know how to, I'll teach you how to write those equations with but before that, you have to study some calculus, like what are the functions, how to differentiate them, how to integrate them to achieve our goals. Okay, so I suggest you to get prepared before I start telling you this about these beams and frames. But now we are talking about just trusses. So we have three assumptions. What is the first one? We assume that the members are pin joint. Secondly, we assume that all the forces are being transferred through the centroid. And third, we assume that all the nodes will and only will receive loads or transfer the loads. These are three assumptions, remember? And there will be a question: what happens to the self load of this, or this is being this is being bended? This self, its self weight is bending it. But what about this? We are avoiding that. Is a purely axial, and there will be only axial stresses whenever we construct it. Okay, we are always in design phase, there will be only axial stresses. So how could that be possible with its own self weight, which is distributed here? How we will calculate that? Because when we are constructing a huge structure of made up of steel, there will be self weight, and which is of huge amount, and that is also being transferred. So we assume that its own weight which is actually, okay, so its own weight is not acting at the cross section, at the centroid of the member. We assume that now actually it is distributed over there, but in simplified, we assume that the all weight of the body is acting through the its centroid. So instead of this, we assume that initially we assume that it is a uniformly distributed. Then secondly, we assume that it is acting at centroid of that. in these two cases there is a bending, but to avoid that bending in our analysis, in our simplified analysis of trusses, we just this is this is its own weight, and suppose it is a this is small, it is a distributed weight which is over acting say L length, then there will be total weight will be WL. Okay, WL there will be in kilonewtons, and here it is in kilonewtons, or say uh, some other unit of force. But to simplify this, we assume that all the weight of this member itself will be acting on both nodes equally in the direction of gravity. Okay, so it is, that's how we will apply our third assumption, and including its self weight. Okay, and whenever we are just applying a payload over it, then what will happen? How will how will we get the force, net amount of force here or load here? We can just uh, do vector analysis on it, and there will be some resultant of it. Not this much actually. You can resolve it. I'll later tell you how to do vector analysis. Okay, so before that all by taking these three assumptions in mind, we assume that a truss is something which is a structure and transfers its loads through the member in only in the axial fashion. Okay, so there will be either compressive force or a tensile force or no force in a structure. So let's say how we gonna analyze that structure. Okay, so we can analyze that truss um, by two methods. What could be our method? We can analyze uh, what could be methods for analyzing. Methods for analysis. I'm talking about all structures at this time. So how we go, what is analysis? Analysis is how much uh, how much and how in which way load is being transferred through the structure. Okay, so how can we just say how it's deforming? We want deform, we want to know how each and every member is deforming under those applied loads. See, so what is the effect of that load on the structure? So we can say example, this is a structure, maybe a cantilever beam or simply supported beam, just say. See, see, this is a simply supported beam. I've just exaggerated the diagram. So how you can analyze this? Either you can take small and small part of it, say this cube, and individually in so many part, and notice the deformation. Just make it in elements. Okay, in elements, so that if you analyze each and individual element of that, say this, if this is that element, And if you are analyzing each member of it, how much forces are being transferred, say forces, moment, shear forces, and all, or the shape of the member, does it changing in that element? Does it changing like this? Okay, what is happening to each and individual element? Then that method is called finite element method. Finite element method. It is a famous method and is widely used in detailed analysis of the structure. So what is another method? You can just don't need to make in simplified analysis. You can just avoid taking each and every element of it, but just paint some grid over the surface. Okay, just paint some grid over the surface and talk about a particular square or rectangle of it. So then our element or the area of interest will be a square, a 2D member. Okay, so what is this type of analysis called? This is called finite boundary method. Okay, in this we just took each and every element, and in this method we just took a particular element. This is called finite boundary method. Okay, then there is another method for which we widely use in undergraduation courses, which is a method of section. Just cut a section at x distance, say if this is x, just cut a section. Okay, and this is called, and see what happening there. And say calculate each and everything in terms of this x. Say it's total load, loads acting relative to this axis, this section particular. And then that method is called method of section of sections. Okay, then there is another method. Either these all methods along with this can be classified in two manner. Either get the forces get the forces and calculate the deformations, or estimate the deformation. Either calculate forces and estimate calculate calculate forces and estimate deformation. Okay, either calculate forces and estimate deformation, or calculate or measure in experiment. Okay, calculate forces and evaluate or estimate the deformation, or calculate or examine the deformation and estimate the forces. Either you can follow a force to get the deformation, or calculate the deformation, or get the what will be the maximum load or desired load was there. So, or allowable load is there. So this method is called force method, and this method is called deformation method or displacement method. Okay, so till now we just see we have noticed these various methods, and now I'm just focusing my attention on in these two methods, method of forces and method of deformations or displacements. So method of forces or force method, in the simple words, in force method in force method we apply loads, or we say this time I'm just talking about trusses only. I am applying loads. Okay, I am applying loads, and if I am applying loads, that is a force, and what will I calculate? I will calculate, in order to get what is the amount of deformation is on it, what amount of deformation is on it or in it, I will need to know the support reaction first, so that I can make a free body diagram and calculate what is the amount of force R acting on that particular member. So these are being applied, and this load is transferring through these two members, and then it is being transferred to the support and this one member also, and this one also support. So how all these are transferring, I want to know that. So I want to know that, or you want to know that, how you can do that is calculate the support reactions. And remember, this is the 2D structure, which is a truss, especially truss. I'm not talking about all others, no frame, no other. I'm just talking about trusses. Okay, so all these forces in a truss are in two mutually perpendicular directions, say x and y. All of these. So this is say joint 1, this is joint 1, joint 2, joint 3. These are three joints, say j equals to 3. Okay, then what will I have? I have 6 forces. To at each joint there will be 6 forces, or I can say these are the 6 equilibrium which I need to maintain. And if I'm saying it is equilibrium, which are needed to be maintained, okay, which are needed to be maintained, then there will be 2 times j equilibrium which are needed to be maintained, or these are the equilibrium equations. What are these? These are the equilibrium equations which are available. Okay. And what are the unknowns? Unknowns are these support reactions which we don't know, mm, like this, this, and this. These are support reactions which we wanna know how much support reactions are being generated. So I'm just saying this is 1, this is 2, and this is 3. And then there are I can apply these equations. These are equations, okay? Then there are support reactions. I am just denoting them with notation R. And what are they? How many them? 1, 2, and 3. R equals to 3. This is the value of R. Okay? These are reactions and this is the value of R. So these are 3 unknowns. Along with them, I want to know how much amount of force is being transferred through these members in each and every one. These are, say, this is M1, M2, and M3. How many members are there? 3 members. Okay, these are 3 reactions. These 2 things which are needed to be answered before applying further analysis. These 2 support reactions and number of members are unknown to us. All what we know, we just know the load acting on the joints, and what we have tool to get these reactions or these values, we have 3 equations. Three sorry, not 3 but 2 times twice of J equations. Okay, so these 2 unknowns. What are our unknowns? If we write an equation, we will have unknowns and knowns. And then we have a relation, say equality. Okay, say 0. So if unknowns and number of unknowns, what I am saying, number of unknowns and number of knowns are equal, then it is easy to find out. Say suppose I have an example, x equals to 9. This is a one unknown and which is need to be determined, or say this, or just complicating problem. This is one unknown, okay, and which is needed to be find out, and only one thing we want to know. Okay, these are knowns, these 2 values are knowns, sorry, these 2 known and these are unknown. If we add them, we'll get net amount is 0. This is single unknown and this is single known. What will happen if I'll just say a plus b equals to 8? Then there is 2 unknowns and only one known. Okay, we got only one equation. So these are number of unknowns are greater than the number of knowns. So what will happen? We'll need a one more equation, and that is the case when unknown minus knowns equals to 1 in this case, and this one is called indeterminacy, the additional required equation. To get the answer, you need another equation, say a minus b equals to something else, and then you can get the other variable. So in order to get this extra equation required, which is called the indeterminacy of the given structure, is defined as number of knowns, sorry, number of unknowns minus number of knowns, and there will be, that will be degree of static indeterminacy equals to number of unknowns, which are m plus r, minus number of knowns, which are twice of j, and this is the degree of indeterminacy, static indeterminacy. Why static? Because we are we are talking about force method. Okay, getting? Good. See you in next lecture. This is quite long. I'll teach you kinematic indeterminacy in another lecture.